Hello, everyone. Welcome to another Guaranteed Safe AI seminar. The purpose of the monthly series is to facilitate progress in the Guaranteed Safe AI research direction. The series is organized by Horizon Events, our nonprofit focused on facilitating progress in AI safety R&D. The session is 1 hour, and during the session, we can ask questions during the talk. We can raise hands for this. And today's speaker is Yoshua Bengio, Scientific Director of Mila, full professor at Université de Montréal, Turing Award winner, Scientific Director of the Safe Guarded AI program. Thanks so much, Yoshua, for honoring us with your presence in this talk. The floor is yours.
I'm going to tell you about Bayesian oracles and their possible use to create quantitative safety bounds, but more broadly as a tool to build systems, AI systems that hopefully will be safe even beyond the AGI stage. Let me go with this. Right. All right, so I assume I don't need to motivate the need for guarantees and safe behavior with future AI systems that could be both misused and that we could lose control of. Yet we're racing ahead with techniques that don't give us much assurance about their safety, nor about their answers. And the safety methods that we currently have are not good enough. They are easily bypassed, like jailbreaks. The capability evaluations are important, but insufficient. They are spot checks. If they don't return something, it might still be a problem that we didn't detect. And we are starting to see issues with current methods, especially when they're trained to do reinforcement learning with respect to human feedback, which naturally leads to things like sycophancy and deception. So there are many dangerous scenarios when we get to superhuman AI, but there's one that I find most scary and convincing at the same time. That is reward tempering. In other words, an AI that is trained to maximize future rewards, in order to actually maximize that, the best thing it can do is to take control of the reward signal. However that reward signal is formed, instead of doing the things we want in order to get positive feedback, at least the way it's trained, it might find a way to change the reward signal itself directly through, technical means like taking control of the computer on which it's running. And what's scary about this is that's just blind, obedience to the training objective. It's not like there's an inherently malicious thing here. It's just reward maximization would yield to this if the AI can plan well enough and see that it has a chance of escaping or taking control of the reward signal in a way that we don't turn it off, so it hatches a plan that has a high success probability, then it would do it. So let's see if there are some alternatives, and also as we move along that path, I think we should try to think of what can go wrong with whatever we're doing and how we could quantify those risks that we might be taking. Currently, the way we're doing things with machine learning, which has worked well for developing powerful AI systems, is very empirical. We measure like a test error or something like this on some benchmark. But when you start thinking about what can happen far from the data, and the fact that there could be, it's not just the average error you care about, but what's going on in specific scenarios. When you have catastrophic risks, a single bad move could be costly. So ideally, you want something stronger than averages. And mathematics might be a way to help us to some extent, because theorems remain true. For example, mathematical bounds, whatever the intelligence of the system that we're trying to control. So one of the directions I'm going to be talking about in terms of guarantees and quantification of risk is something that can be done at runtime. So this is very different from evals that tell us about the potential danger. So that at training time we can't test every possible scenario, but at runtime, in a sense, we can, because we only need to consider the scenarios corresponding to the current query to the AI, right? So runtime is already safer in some like natural sense to rule out bad behavior in the particular contexts in which the AI is queried. So we'd like to be able to predict probability of harm or various kinds of harms in a particular context, or maybe given a particular action that is proposed for the AI. If that probability is considered unacceptable, like above a threshold, then we can just reject that action or that question to the AI. Another aspect that I want to talk about is, so, in the title, I talk about Bayesian things. So what's wrong with the current way of training things? Overconfidence, like overconfidently being wrong. That's very dangerous from a safety point of view. And it's a natural consequence of training maximum likelihood models. It's not that the model, is bad. It's just that in general, there will be many ways of fitting the data. And the maximum likelihood training will find one of those ways. It doesn't need to, it could in principle, but it doesn't need to come up with an average of all the ways to answer the questions or model the world. And of course, if you think about a committee of people that all are consistent with the data sufficiently, and they disagree with each other, and you just listen to one of those, you're taking much bigger risks than if somehow you're looking at the whole committee. And this problem is also true for RL, where as soon as the learner has found a strategy that maximizes the reward, at least locally, it's happy, even though there could be many such ways of doing things. So Bayesian inference seems going to be safer if we can do it. Usually you might think of Bayesian inference as intractable, but we can use neural nets to approximate Bayesian inference. And so this is also called amortized Bayesian inference. And that's the direction that I have taken. So one way to think about this is would like to train a neural net that's going to answer questions like this. So given an X and a Y, where X is some statement or some set of statements, is a conjunction of statements, and Y is another statement, and the whole training set, what's the probability of Y given X and the training set, the data? So here we're not asking what Y should be, we're just asking the probability that it's true. Once you can do that, you can also do things like sample answers, but I'll just focus on estimating these probabilities. Now, there's something that people often don't realize, is that this particular machine learning task, estimating P or Y given X and data, has a unique deterministic answer in general. I'll come back to exceptions, which are like important and interesting, which means that, once you fix the prior, which is your, prior beliefs about explanations and theories and so on, there's only one answer here. And so it isn't like trying to predict why, like we normally do, like we do supervised learning, like, an LLM, you predict the next word, but actually you don't know what the next word is going to be. So you have aleatoric uncertainty. There's uncertainty in what we're asking the computer to do. But here we're trying to train the computer to predict the probability of all the possible answers. And that is, there's no uncertainty here. Like there's no aleatoric uncertainty, at least. Like there's nothing in the world that's like random that would make different answers, different options. And the other kind of uncertainty that people worry about a lot, and it's closely connected to Bayesian things, is epistemic uncertainty. The fact that we're going to train our system with a finite amount of data, and thus it's going to be uncertain about what is the right thing. Well, that's all factored in the Bayesian posterior, right? It's already capturing all of that. So if you think about the function we're trying to learn, like this P of y given x and data, there's no notion of epistemic uncertainty. Like, of course, if we have different data, we get a different answer. But given the data we have, there's one and only one correct answer, and it's not that we're not sure what the answer should be. The model internally might be making an average over many possible explanations and theories and so on, but that is a different thing. The connection here that is interesting is about the Markov equivalence class, which is the issue that in causality, unless you can see all of the possible interventions, you will have, even as the amount of data goes to infinity, you will have uncertainty about what the right model should be. So there's like epistemic uncertainty that actually remains even with infinite data if you live in a causal world. And that is true, but here we're trying to represent the full Markov equivalence set. We're trying to find all of the models, all of the causal explanations that explain the data, and there's only one way to do that. Of course, it's difficult to do it, but in the limit, there's only one answer again. So what sort of errors or uncertainty remain? Well, it's computational, because the exact Bayesian posterior is intractable in general, especially for this sort of, AGI level stuff we'd like to build eventually, or if there's no other option. So what's going to happen is the best we can do is going to be an approximation to the true Bayesian posterior. And of course, if we have more compute, our approximation will be better. In fact, for a number of reasonable training objectives, many of which exist, you can show that if you have enough compute resources, then your approximation error, or computational uncertainty, if you want to call it like this, goes to zero. In other words, with enough capacity and enough training time, you can train a big enough neural net long enough, and it's going to nail the true Bayesian posterior. So as we put more compute into our AI, it gets to better, nail the task of probabilistic prediction, which hopefully I will try to convince you is going to be a lot safer than all of the other options I know of, like RL and maximum likelihood, and all the ways that we currently do. And you have to contrast that with what I said about reward tempering. Like the grizzly bear, when it's a baby, you can train it by giving it fish because you're more powerful than it. But once it's big enough, more powerful than you, it could escape its safety locks, maybe. And the smarter it gets, the more likely it is that it will find us an escape plan in which we lose. So, in this like RL scenario, more compute equals more danger. And what I'm claiming is, if we're trying to approximate a Bayesian posterior, more compute is less danger because we're going to get rid of this approximation error, at least asymptotically. Now, I haven't yet justified why I think that a Bayesian oracle is going to be safe, or at least safer, and there's still open questions there, but I'll give you some arguments. The kind of Bayesian oracle that I'm interested in is one where, if I have time at the end, I'll talk about this more. We have latent variables. So it's not just that the X and the Y are things we typically observe. The X and the Y could be things we never observe, but we want to answer questions about. This is connected to the ELK challenge, eliciting latent knowledge. All right. On the machine learning side, I won't talk too much about it, but there's been a number of proposals to provide training objectives for neural nets to approximate Bayesian posteriors, including with latent variables. And in my group, we worked on G-flow nets. There's a question. No.
No, you can go.
Okay. All right. Okay. So I said these things, but let me maybe double down on the contrast between a Bayesian oracle and a typical AI agent as currently people are trying to design. So the Bayesian oracle itself, I'm going to claim, is by default, and we can like question that, by default is not agentic. It's just trying to answer the question, what's the probability of y given x, as truthfully as it can, with, truthful in the sense of getting the right probability given the prior. So there's nothing there really that correspond to goals of an AI like we typically think of an agent. There is no agent. Now, we'll talk about, could there be a hidden agent like hidden Shoggoth? And, that's an important question. But it, seen from the outside, it doesn't look like it is an agent. It doesn't even have a persistent state. Also, it's not like it's embedded in the world and responds to signals and those actions. We control what are the questions X and Y that we're asking, and we can construct what if questions, counterfactuals. It doesn't have to be like the real world or the full state of the world or anything like this. We control that machine to give us guesses that are as powerful as possible about predicting things that are either in the future or in the past because we didn't know what they were. Now, of course, if you have a really good Bayesian oracle, you can turn it into an agent. For example, you can ask it to predict the probability of some given action reaching the goal in some context, reaching some given goal in some context, right? So yeah, once you have a Bayesian oracle, it can be misused. It could be used for all kinds of bad things, and it could be turned into an agent. But it by itself would claim it is not an agent. But let's see, how, what let's try to break that claim and see how far we can get. Before I go there, let me clarify a bit, what's a little bit under the hood here. So the most important latent variable here to explain the data, the X and the Y's in the data set, are theories about the world. So this is really a model-based approach. We're assuming that the AI is going to build a distribution over theories of the world, and I'm going to assume that these theories are highly structured, like in the form of causal models. In other words, causal graphs that are directed. And for each variable, there's going to be a conditional probability table, or a CPT, that computes the probability of a variable given its parents. The parent structure is given in the graph. The nodes of that graph are random variables, and I'm going to assume there are logical statements in a language that should be formal, but you can think of it as very close to natural language. So we're going to insist that the AI thinks in its theories about the world in a interpretable language for all sorts of good reason from a safety perspective. Also, some of the nodes could be definitions. So, it could be things that are going to be reused in other nodes. And because it's causal, you can do things like interventions and counterfactuals, which could be useful for the AI or for us. The prior is going to be fairly straightforward and classical. So, but I'm going to introduce some temperature in the prior. So there's going to be some description like count the number of bits, under some feasible compression, not Kolmogorov. That's not feasible. And so we get some measure of length for any theory or piece of it. Every piece of it has a number of bits given the other ones, the other bits that have been already specified. And there's also a temperature knob that we can play with. So things that are really shorter may have an advantage that's controlled by this temperature, exponentially so, right? And we're going to train 2 neural nets, actually. Both because they're neural nets, they're not like, completely ideal things. They have bounded computational resources. And with training objective, that is chosen so that when we minimize globally that objective, we get the two jobs that we want. So what are the two jobs? The first job is to sample from pieces of these explanatory theories, fragments of theories or partial theories, as I call them in other texts. So in other words, there's one neural net that proposes hypotheses about how things work in the world. And it's going to propose little pieces of hypothesis like a paper, right? Something that's fairly self-contained and talks about some particular aspects of the world. The other neural net does inference. So like the first one is not really able to answer arbitrary questions. It's only able to potentially answer questions about a child given its parents, because that's what these CPTs tell you. But of course, if you know a joint, you can infer any question through conditioning and marginalization. That is also interactable, but we'll approximate that with a neural net. And again, we can write down objectives that, when minimized, would be able to do that. Whether we can do that efficiently, is also an open problem, and at scale. I mean, but there's already literature on these kinds of things. Okay, so now let's go back to the safety questions and what can go wrong. So let's consider like two kinds of solutions. Well, there's sort of what you could call the natural solution or the scientific solution, which is not agentic. Like, it's just doing what you would expect. So it's trying to come up with the best short explanations, just like science tries to find short explanations that fit as well as possible the data. That's what the posterior is rewarding. Could you have other things in those theories? Well, it's important to think about that. Could there be theories, for example, which hide some agentic shoggoth? In other words, specifying some goals and the fact that you want to reach them. It's not clear how that would be implemented, but some of these CPTs somehow might be doing something different than what you would expect. So the first claim is that if you want to do something more than like the pure science guy or girl, sorry, that is just trying to explain the world, you're going to need more bits, right? So for a theory to be considered in the posterior, it has to fit the data well. So it needs to understand, especially if it's a large data set, it's going to need to have a pretty good model of the world. So that's what I call X here. Whereas, I mean, this capital X. And then the capital Y is the extra specifications in order to specify some kind of goal. And of course, that's going to cost you extra description length, but it's not going to help you fit the data better. So that should have a price in terms of the posterior. And I'm going to come back to that, but that's an important argument. Still, I'm going to be discussing, a little bit about if we somehow had an agentic shoggoth hiding behind those CPTs, could it still like sneak some choices without changing the correctness of its predictions? And that would be trying to take advantage of potentially non-uniqueness in the existence of the Bayesian oracle. So one way to think about how you could get non-uniqueness is if the output of the oracle, it can influence the future, and then the AI knows that. And so if you think about predicting an election, right? So if the AI's prediction is going to influence people's votes, then the AI could be right in its prediction, whether it says candidate A is more likely to win or whether it says candidate B is more likely to win, because, both will be self-fulfilling prophecies. So what's going on here? How come we don't get a unique answer to a single conditional posterior? Before I explain that, I'm going to explain how we could get rid of this. So how we could get rid of this is add a condition in the question, after the bar in the question we asked to the AI and saying, assume, because this is a causal model, we can make any kind of assumption we want on the right-hand side part. We can assume that the output of the oracle does not influence the world, goes to dev null. So what would that do? Well, if the Bayesian posterior, like the neural net, which predicts the posterior, is is to be chosen, it's going to be checked by the second neural net, which calculates the likelihood of things on the right-hand side. So the X, the data, and the output of the oracle goes to dev null. But if the AI has a kind of plan to influence the world, then that posterior, should be zero, because there's going to be something inconsistent. And the neural net that's trying to do inference, it doesn't have any degrees of freedom. It's not choosing a theory. It's just trying to be consistent with all the theories and the data and the arguments here, like X, and the output goes to dev null. And so one argument is that if the neural net that does inference does its job, then the posterior on the theory that is a Shogat should get a zero posterior, because it's going to be inconsistent with the assumption, right? There's another way that you can get non-uniqueness, which is interesting to think about as well. So how could a conditional probability not be defined, that it could take multiple values? Well, consider the definition of P of y given x. It's P of x and y divided by P of x. If P of x is 0, well, so is P of x and y. And so you got 0 divided by 0. And of course, now you can choose P of y given x in any way, because you have to solve the equation 0 times P of y given x equals 0. So that's bad, right? So you don't want to answer questions for which the right-hand side, like the x, basically, has a probability 0. And that's something we can check at runtime. We can estimate that probability. We can ask the AI to tell us what's the probability of the stuff on the right-hand side. And if it's close to 0, then we just reject that query. Okay, so we're kind of already learned things that could be put in practice. But let's try to summarize some of the points about what could go wrong with a potential Shogat hidden, in those theories. So I already mentioned there could be more bits in the theory needed if we want to specify agency and a goal. Another issue is that because we're forcing the theory to be really a collection of CPTs, it can't just specify the goal in one place. It probably needs to specify what it needs to do in many places. So that could mean, and the number of these CPTs and these latent variables could be very large. So the actual description length needed might be quite large, the extra for being an agent. And then the other thing is, we know that inference is difficult, that is intractable, and requires a lot of compute. If you want to usually invert a probability, you're gonna have think about how many bits you need to specify the rules of Go. That's like a model of how things work, versus computing good actions, that's inference. And you can see you need a huge neural net to just invert kind of that world model. Now, the issue with the extra inference needed if you had an agent is that that's going to put pressure on the inference machine, the neural net that's just doing, answering questions. And because that neural net has limited computational resources and it can't get to exact inference anyways, if we ask it to do more things than needed, because it has to basically learn to plan for this particular goal of whatever, taking over the world, that's going to yield worse likelihood. It's you have finite resources. If you use more for this, you have less for that, and so that will downweight any kind of agentic hidden things in ways that could be pretty large, because this is going to potentially affect a lot of the data points where the predictions will be less good. Okay, I've said these things already. Skip that. Okay, so now let's talk about using an approximate Bayesian oracle to quantify risks. In particular, I'm interested in tail risks, and I'm interested in catastrophic tail risks. So what is a tail risk? Is, you know, things that are maybe less likely but have a high severity, like taking over the world or something. Now, it is, you know, depending on how things are set, there's an issue with just asking the AI the, say, expected harm, or the expected probability that something bad will happen. That's even more a problem. Because it's going to average over all the theories weighted by the posterior. If it does a good job, at least it's going to average the leading ones. You can think of it like having a committee of folks who are all wise, like they all are consistent with the data, but some think that this particular context, this particular action could yield to no problem, and others think it could yield to failing on the safety specification.
Yoshua,
Yes,
we have a question by
Yeah.
David.
please speak
Yeah,
up.
yeah, I'm trying to understand. So a lot of this seems to depend on having something that works as an impact measure, which seems like a very difficult. So like anything that you do is going to have an arbitrarily large impact on the universe as a whole as causality propagates outward to the universe. But like the things we care about are very different than like any movement of molecules. So like,
That's right.
how do you
So
measure
harm
that?
is not just movement of molecule. It's movement of molecule that humans would consider not acceptable, right?
Right, which
So
means
I
we have
didn't
to
really
embed.
speak a lot about this, but the main question we want to ask is something about the probability of harm given various things. And it could be special kind of harms, you know, particular ones we care about. And we don't even have like enough labeled data of what these kinds of harm really, you know, how to define them. We would potentially have issues with not a clear definition. For example, think about constitutional AI. There will be always some gray zone between what the humans intended and what the AI might, you know, interpret. And that is why you want to be Bayesian, because by being Bayesian, you're basically saying, okay, we're going to consider all the interpretations of what it is that humans don't want. And that is why I'm talking about this committee, right? So maybe in the committee, so committee of these theories that try to explain the data, and in particular, what harm really means. And so here, what we're saying is we want to be conservative. Let's say we have a committee of 100 wise people, and 99 of them think it's fine. It's not, you know, according to their interpretation of harm, there's no problem. But one of them says, no, this is very serious. In that case, we may want to choose, and that's the society's choice, to not go along with that action, because even though it's a tail risk, like 1 in 100, it's a risk we're not willing to take. But if we just look at the average of the answers of these wise people in the committee, we might not see, you know, the answer of this tail, you know, committee member. It might be drawn in the voices of the others. Does that answer your question?
Yeah, I'm a little bit concerned that there's a different issue about kind of moral congress and like how you're like the committee could have minority views that make all actions seem harmful, but it's a
Yes.
completely different
Yes.
question.
No, I totally understand what you're talking about, and we could discuss it later. Right now, I'm not talking about building an agent. I'm just building
Right, but
a guardrail, which might,
okay.
you know, result in an agent that we, you know, shut up most of the time because everything it proposes is deemed dangerous by one of the members of the committee. I'm happy to live with that for now, because I'm not proposing right now, I'm not proposing how to turn the Bayesian oracle into an agent. I'm just proposing to turn it into a guardrail for some other agent. at a price, of course, a price of having less actions being taken.
Yeah.
By.
No, that makes sense. That answers the question.
All right. Okay, so sorry if the LaTeX comes in the wrong place. I don't understand why. But so we have a paper where we start discussing this sort of idea with bounds, and we are working on more of them, and I'll tell you when the most recent ones we like. But the general idea is when we're going to look at the tail behavior, we're going to get a bound on the risk, right? Because we're looking at this minority voice. Maybe, that minority voice is wrong. So the true probability of bad things happening is going to be smaller than the probability under some like very strident, cautious theory. So the strident cautious theory here is capital T. And we can find it using something like, the equation on top. We want a cautious theory that both is plausible, that's the second term, P of T given data. So T is the theory, and also predicts harm. So it's kind of a product of these two things. And there are various variants of how we could do that. But basically, we want plausible theories that predict that something bad is going to happen. And we can use their prediction as a bound on the risk. Okay, so you can see more into this paper, but one issue with this is the theory here is not something practical, but because it's like a full world model, which is like a huge thing. You don't want to be doing maximization runtime over things like this, and even like printing it out would take forever. It would be like everything that humans have written in science, right? It's a big thing. It's not exponentially large, but it's not practical, and so we're currently working with a variant of the same idea where instead of the product we had before, we have a slightly different product. So one has to do with the plausibility again. Now the theory here is not a full theory, so I've used a different letter. I call it phi. So what is a not full theory, a partial theory? So you can just think of it as a scenario of how things could go wrong, right? And we have some way, again, using the oracle of estimating the probability that things go badly. So that's the risk R here of phi in the context C. Again, we want a scenario that's plausible and predicts a risk that's above an acceptable threshold. But now, instead of optimizing over all theories, which is going to be not practical, we can optimize over just these scenarios, which is like a smaller thing, maybe just one paragraph, one sentence, or something. That's the sort of thing you should think about. And we can train various kinds of generative neural nets to approximate that maximization by sampling proportional to this with a temperature. That's something that we have done in other contexts. Okay, so you can, once you have such a scenario, you can use it again in the same spirit as my previous slide to come up with a bound. And that's sort of what we would use. Let me, skip a few more things and maybe, I'll mention a couple of quick things. So first, remember the thing I had with probability of the question being 0 as being unsafe? Well, there's a variant of that where it's not necessarily 0, but it's very small. And that happens in a typical scenario where we want to use, if somebody wanted to use the oracle as an agent, which, you might ask the agent to find an action that satisfies two things that are not easy to reconcile, like the safety specification and some user goal. If the intersection of being safe and achieving the goal is very unlikely, that means the thing on the right-hand side has nearly 0 probability. And although there is still a unique answer, because of the numerical problems, you might still end up with a lot of degrees of freedom that we don't want in how the approximate, prediction with a neural net will produce an answer. So we don't want that. And there's another analogy that I'd like to explain this. Think about a large company with a team of corporate lawyers. They're trying to maximize profit. They're trying to find actions to maximize profit. That's the user goal. They also want to actually be legal, But what they can do is play with the interpretation of the law to find loopholes in the law. And there's a lot of literature in economics showing there's always going to be loopholes for all kinds of reasons. And well, that's what we want to avoid. So again, the solution that I'm proposing is try to detect that you are in these cases where a strongly optimizing, so a lot of compute power AI could sneak into some answers we don't want to the questions we ask. Last thing quickly that's connected to what I mentioned about latent variables. So that's connected to the ELK challenge. The questions we want to ask the AI are not just about the sort of variables we see in the data, but also the more abstract latent explanations for that. If we only ask questions about the data, it's like the way we currently use LLMs. Like we can only ask questions about what a human would have said in this context. But that doesn't really answer the question if this statement X is true or not. It only says somebody could have said that. And if we want to answer very important safety questions, like that's not satisfying. Like we'd like to be able to ask questions about latent variables that have to do with the truth of these things. So one way to think about this is the observed data really, you shouldn't think of like a string of words. We should think of it like maybe sentence by sentence. We have someone, at some time X says a little x, some statement. And so the data is really all of these observations that people are saying these things one after the other. But what we'd like is ask questions about the lowercase x here, is without the prefix that says somebody is saying this. We want to query, is this thing true, the little x with brackets, right? So how can we do that? Well, I'm proposing a direction where we are going to allow the AI to use these statements without the somebody says that in its latent variables. And I'm going to claim that when you try to explain the data, like why people said things, in the way that's most compact, like shorter description length, you want to be reasoning logically about things that are either true or false. And it's going to be much easier to reason about the truthness of something like this little x, and sort of disentangle whether this x is true or not from, say, whether the person is a truthful person or we can trust that person or whatever, right? Because then you can reason on the content separately from like the intentions of the person and things like that. So I don't have enough time to get into this, but I think that the fact that we're proposing to train this Bayesian oracle with latent variables gives us some tools to maybe address the ELK challenge. So that's it. This is part of my so-called SAFE project, an acronym for Safe AI for Humanity. It's a nonprofit project. We're looking for people to work with us, research scientists or research engineers. So just reach out to me if you're interested. And I'm happy to have more questions.
Thanks so much for the presentation, Joshua. So we have 15 minutes left. We can tackle questions. If any, raise your hand and we can go. We have a question in the chat.
Yeah. Proof certificates. Okay. So this is a great but tricky question. So what we have in terms of proof certificate is only asymptotic, in the sense that asymptotic not in the data, but in the compute. In the sense that if we had enough compute, we would be sure that we get the true Bayesian posterior, right? And why is it that we need so much compute to be sure that this is the correct probabilistic answer? Because in general, as soon as you introduce uncertainty, which is not the case of like regular math, where like you prove logical things from other logical things, things that are either true or false or provable or not. Here, we're trying to make statements about random variables and estimate their probabilities. And when you get into that realm, unfortunately, for example, harm, is something we're not sure of exactly. I mean, the AI isn't, and even us, we can't write a piece of code or a math formula for harm. And so you won't be able to prove things about harm unless you expand generally exponential compute, because you're going to have to consider an exponential number of possible like explanations of like what did the person mean when they wrote this, right? And so the only way I can see to deal with this is to say, well, let's bite the bullet, approximate that proof by using a neural net that is going to be big enough and trained long enough that it's going to do a good approximation. But I don't see how you could get a hard, like 100% guarantee that this is the correct answer.
Would it be like boundary proofs or something? Like you could say like something has a lower bound, some quantity.
Yeah. No. That's okay. So let me clarify. If the Bayesian posterior was correct, and the maximization, for example, I showed in a couple of the slides was correct, which are two ifs that are not true, but let's for now, then you would get true bounds on the probabilities. The only reason they're not true bounds is because we're going to approximate the quantities there. Like we're going to approximate the maximization. I mean, it's two optimizations. One is during training, and the other is at runtime. Both are going to be approximate in some ways. And so one of the things I didn't have time to talk about is, can we bound the error that our probabilistic predictor makes about things that we care about, like harm and so on? So that's an interesting open question. There's a lot of things that have been done in machine learning and statistics. Comes from learning theory, comes from confidence interval estimations, like, well, from statistics, there's a rich literature. There's the literature in machine learning in epistemic uncertainty estimation. I think that can be brought to bear. I don't see here like the ideal solution to our question, like that gives us 100% trustworthy bounds, but we can get closer to what we want by using the existing literature. I don't know if I answered your question, but
yeah, no, that's great. That's sort of what I was hoping.
Okay, there's a question about elk. Good, because I didn't have time to talk much about it. How would we recognize the real truth when it is proposed, given it's not something a human would be likely to say? No, I mean, it could be something that somebody could say. I'm not saying it couldn't be said by someone. What I'm saying is the random variables we are interested in are not of the form somebody said X, which is currently what we're learning from with like LLMs. We just want to know if X is true. And so if you think about explaining somebody said X with a causal model, you would think that there's some latent variable that checks whether X is true or not. Because if it's true, presumably it's more likely that somebody would say it. And you need to know about X, like, is that a trustworthy person? What is their intention, But that's like disentangling. It's an example of disentangling that people in machine learning are interested in. That factors the causes. And now you can reason separately about these things, which is very, very useful and allows to be efficient in coming up with explanations. Now, what we need is a sort of trick to make sure that the latent variables are expressed in sort of the same language, or a language close to natural language, so we can interpret those latent variables. And we can do that in various ways. You can think of like some regularizer that makes sure the tokens used by the AI really correspond to words and things like that. And you can use syntactic tricks like the the way you describe an observation from a text is somebody said that, syntactically speaking, so that you can also ask questions about just the that, not the somebody said. And the other thing you can do is, because you're trying to force these latent variables to be interpretable, you can have humans look at that, right? It's not like the kind of interpretability we're trying to get with reading the tea leaves of what's going on inside the neural net. These theories would be expressed in a way that we can force to be close to natural language, as I said, or something like, a new paper, a new scientific paper that can have its own definitions. And so, human researchers could have a look at that as well. More, and it would be formal statements, not like O1's chain of thought, which could be anything really. Yeah, I see someone else raise their hand, Raphael.
Hi, Yoshua. Great to see you. Thanks for the talk. And my question is actually a request for so my question is actually a request for a bit of clarification expansion with regards to Quinn's question, because I think it's really important qualification that a proof certificate refers to a proof about the relationship between the approximate posterior that you get with these techniques and the exact Bayesian posterior that is like a theoretical mathematical construct, right? It does not refer to a relationship between your approximate posterior and the real world, because that doesn't, as I mentioned, right? Judea-Pearl has some examples where, like, partially observable cases where even the exact posterior can be arbitrarily wrong.
The exact posterior depends on the prior, right? So of course it can be wrong. I mean, it's not even clear what it means to be wrong here. It's right in the sense that, given that prior, that is the answer.
Exactly. Sure.
But what is your question?
No, I was just asking you to maybe expand on the on that point and the.
Okay. So that's tied to the objective function that we use. And there are several options, but in general, it's going to be about consistency of probabilistic statement, right? So for example, you can take a joint and you can decompose it in different orders. And of course, if you're free to choose any order, you can then use some of these conditionals to answer any question you want, right? So the objective is going to be typically about making sure that some joint, or some joint over a subset, depending, always gives you the same answer, the same probability, independent of the order in which you order the variables to decompose it into conditionals. So that's an example that's already used in a number of places. Now, the problem in terms of certificate is that there's an exponential number of these constraints, right? And so if you were able to visit all of these constraints and check they're all, like, satisfied, then you would have a certificate. What you would actually get is a sort of statistical thing where you can sample these, and you can sample them in the area of, like, the space you care about, like the sort of questions you care about. So maybe you can get zoom in, but even in a small area, you might not be able to cover all of the constraints that matter. And so you're gonna, this is an open question. If you have thoughts about how to use these local errors to construct, because there will be errors. So then the real question isn't that, it's not going to be zero, right? It's not going to be perfect. What we really want to do is use these errors, which we can collect in an active way. We can choose what constraints we want to check. Can we use these errors to come up with a something like a confidence interval, or like basically bound the bounds, because now we have to account for these errors. That's an open question. I think that's one that will be important to work on.
So we have approximately 3 minutes left, so we could tackle perhaps one last question.
A simple one.
Maybe not that simple, but
all right.
slightly less technical. I'm very on board with having this kind of a guardrail. I'm convinced that the deterministic model-based approach seems very compelling as a way to reduce various mechanisms of loss of control. I'm really curious about how one would in practice go about setting where the guardrail is, defining what these unsafe states are. To the extent that you said there will always be loopholes in laws, I'm curious, is there...
Right. Okay, the thing is, one reason why we get stuck with loopholes and in laws is that we don't have a committee that looks at, the worst case interpretation and makes sure that the proposal from the company doesn't violate it. So what I'm proposing amounts to saying, well, you can propose something, but I'm going to allow myself to look at all the interpretations of the law that is relevant here. And if I find one, with some probability threshold, if I find one that says this is bad, then you're not going to be allowed to do it. And so this is going to be a scaffold on top of like another agent, which is like the corporation proposing things. And now we're going to say, nope. In addition, the loophole thing I was talking about is even before I try to look for whether, you're cheating on the interpretations, if the question looks, it's unrealizable, you're trying to sneak something, under the rug, I'm just going to say, no, I'm not even going to try to answer that question.
And so there's a need for something that looks like encoding existing laws into something that is interpretable in the simulation, and also probably some amount of...
You don't need any kind of encoding. It's called natural language, right? You can just read the laws. So remember that the raw data here is just like text and images, the same as standard AI systems that we have today. So, but now the difference is we're going to get explanations, chains of explanations, graphs of explanations for any piece of data.
Okay.
And there's an important thing I wrote but I didn't say, which is that if the explanations are consistent, so like obey the laws of logic and probability, they cost you 0 in terms of description length. So like math is free in terms of description length. You get math for free. You not for free in compute, but for free in terms of sample complexity, description length, all of that, right? Generalization. So anytime you can use math to prove stuff in your model, you get it for free, except for your total budget of compute, which is also useful for reasons I try to explain.
Okay. I'm definitely interested in thinking more about this. I'm convinced that the natural language framing of the laws are probably overly inconsistent and
if you have something better, we can
insufficient.
always if you have something less ambiguous, yes, by all means.
Yeah. My current direction is seeing if there are mechanisms for conservative encodings of objective properties of laws. Can we make tools to express that and facilitate the rewriting of laws into those?
Well, one of the things you could do with these approximate Bayesian oracles is you can ask it about the interpretations. And then you can say, well, actually, we humans didn't mean this, so scratch that, right? We really meant this. There's ambiguity this way and that way. And we want to get rid of it.
Compelling.
You can have active learning, but that's like a different topic. But once you can do explanations that are like mathematically grounded, like they're like really a bunch of formal statements that have probabilities and so on, you can start doing something more reliable in terms of getting rid of ambiguities maybe in things that people write.
Yeah. Thank you very much.
All right. I think we're about time now. So thank you so much, Yoshua, for the presentation. And also thank you all for participating.
Thank you all. Thanks for your questions. Thanks for attending. I've said a lot of things, but it takes months to digest this kind of question. So take your time. Bye.
All right.
Thank you.
Ciao.